part of the lab time to talk about chapter 17. Are there any questions then? Started? No? Alright, so we're going to continue with our mixtures. So we spent a lot of time talking about this type of mixture, the weak acid, weak base mixture. How many different types of weak acid, weak base mixtures are there? 3. And then what are the 3 types? Yeah, weak acid with its conjugate base, or weak base with its conjugate acid. So conjugate pairs, that type of weak acid, weak base mixture would be called a Henderson-Hasselbalch buffer. Actually, all the weak acid, weak base mixtures are buffered because the acid and base coexist in solution, so it's capable of neutralizing added acids and added bases. And so the 3 types, one is the Henderson-Hasselbalch buffer, which the acid and base are conjugate pairs. What are the other types? Another type is where the acid and base are unrelated. Like ammonia and acetic acid. You know, those aren't conjugates of each other, but they aren't going to completely neutralize each other out.
Is there one more? Isn't it?
Amphoteric is the last one. It's the last one is where they're the same species. And so the acid is the exact same species as the base. And the only time we can have that is when it's an amphoteric ion. And so any amphoteric would be like this. All right, let's look at some other mixtures that we're going to encounter. One of the other types of mixtures would be something like a strong acid and a weak acid. Strong acid and weak acid. An example of a strong acid, weak acid might be something like HCl and acetic acid. We have HCl and acetic acid. How would you deal with this? Well, this you would treat just as any other acid solution. You'd look for the largest contributor of hydronium, which should be HCl, and then just keep adding the additional hydronium you get from acetic acid and the additional hydronium you get from water. And so the typical way we deal with this is stepwise, you know, starting off with the biggest K and then working our way down. It turns out, because of the common ion effect, when we're dealing with pH, you know, these types of mixtures are very similar to polyprotic acids. When you're dealing with pH, you know, the most hydronium is going to come from step 1. And these types of mixtures, if you had something like 0.100 molar HCl with 0.100 molar acetic acid, practically all the hydronium comes from HCl, and a very small amount comes from acetic acid. So small that your book says you can pretty much ignore it. It's going to be a negligible contribution, especially with the common ion effect. You know. But you can't always ignore the weak acid, especially if the weak acid is a fairly strong weak acid. And so if we did HCl and oxalic acid, you know, oxalic acid is borderline strong, right? It's still weak, but when you look at the K value for this, what is the K value? Oxalic acid has a K1 of, I think 5.4 times 10 to the minus 2. Is that right? Yeah, 5.4 times 10 to the minus 2, which means it's pretty strong, you know. And then the Ka2 is 5.3 times 10 to the minus 5, so it's a bit weaker. Whereas here, acetic acid has a Ka of 1.8 times 10 to the minus 5. And so, you know, something like oxalic would be expected to be a more significant contributor of hydronium. So in that case, you'd probably worry about the contribution of hydronium from oxalic acid. So let's take a look at a mixture. And so this calculation, we're going to look at a solution that's going to be HCl and oxalic acid. And there are two starts to chapter 17 type problem. One is where we can skip step I, the initial solution dilution step, and just go straight to step 1, whatever that is. And 2 is when we have to do a solution dilution step. And so as an aside, you have to be careful because that you have to be careful because sometimes I might say something like this: equal volumes of HCl and oxalic acid are combined. All right, and so there are two starts. There's a start where in the same beaker, it's going to be 0.100 molar HCl and 0.100 molar oxalic acid. And so if it's in the same beaker, then no step I, no solution dilution is required. But if we have something like this, then we have to do solution dilution. And so that means that the HCl is not going to be 0.100 anymore. The HCl should be, well, if we combine equal volumes, then it's a 1-to-2 dilution. And so the HCl will be at 0.0500 molar, half the concentration, and oxalic acid would be at 0.0500 molar. And so we do this extra step here. And so you'll have two types of problems, you know, the ones where the concentrations are given, and others where, you know, in other words, you have a one beaker with the concentrations versus a two beaker with the concentrations, where you have to calculate the concentrations upon mixing. All right, so what we're going to do is we're just going to go ahead and assume it's 0.100 and 0.100. And so we'll do this one here. So if we do this, we want to start off with the biggest K. The biggest K is going to be HCl. And this is an acid solution. This is just a mixture of acids. And so we look for hydronium ion producers. So this will produce H3O plus Cl minus. K for this is going to be what? Yeah, K is going to be very large. And so we'll just start this assuming nothing's happened. So we have 0.100 molar HCl, 0 and 0. The change is going to be complete, so we're going to go down to 0 molar HCl and 0.100 molar hydronium and 0.100 molar chloride. Okay, now is oxalic acid going to contribute much additional hydronium to this? Well, let's see. So oxalic acid will hydrolyze water to form hydronium and hydrogen oxalate. K for this is 5.4 times 10 to the minus 2. When you look at that K value, the K value is kind of big, isn't it? And so this could be a contributor of hydronium. And so the initial change equilibrium, we're going to have 0.100 molar oxalic acid. And then what we're going to do is we're going to drop the hydronium from step 1 into step 2. So this will be 0.100 molar, and this will be 0 molar. But then again, there's a common ion effect. With the common ion effect, we don't expect to generate as much hydronium as we normally would. And so there's, on the one hand, I would think, it's going to be a negligible contributor because of the common ion effect. On the other hand, I would think it might be a significant contributor because of the K. K is kind of big. And so since there's this uncertainty, I would just go ahead and do it. And so this would be plus X. So at equilibrium, I have 0.100 minus X molar, 0.100 plus X molar, and X molar. And so K is going to be equal to the hydronium ion concentration times the hydrogen oxalate ion concentration divided by the oxalic acid concentration. And so this comes out to 0.100 plus X times X divided by 0.100 minus X. I would just go ahead and use the simplifying assumption, even though it might not work. It might not work because the K is kind of big, but it might work because we have the common ion effect. So since it's uncertain, might as well just try it. If it fails, then we'll back up. And so that means X is equal to 0.054 or 5.4 times 10 to the minus 2, which means it's going to be a 54% change. A 54% change is too big, and so it failed. And so even with a common ion, the K was too much. All right, so if that failed, then that means we have to get this into quadratic form and use the quadratic equation for this. And so I'm going to get x squared plus 0.100x is equal to 5.4 times 10 to the minus 2 times 10 to the minus 1 would be times 10 to the minus 3. So it's going to be 0.0054 minus 0.054x. And so we'll get this into quadratic form. X squared plus 0.154x minus 0.0054 is equal to 0. And so x would equal what? Does somebody have a quadratic solver? You got it? What is it, your x value? Okay, yeah. So A would be 1, B 0.154, C would be negative 0.054. 2.94 times 10 to the negative 2. Thanks. 2.94 94 times 10 to the minus 2. And so this is going to be 0.100 minus 0.00294. Is that right? Oh, times 10 to the minus 2. Not 10 to the minus 3. So 0.0294, which is going to give us 0.0706 molar. So in other words, we have 29.4% reaction for hydrolysis in step 2. And so that means we started off with 0.100 here, but we're going to gain plus 0.0294. In other words, we're going to gain about 29.4% more hydronium from this step. And so this is going to give us 0.1294 molar. And so did we gain a significant amount of hydronium from the weak acid? Yes, we did. Your book is going to say, yeah, the weak acid is going to contribute negligible, so just ignore it, right? But there are cases where you can't ignore it because it's significant. And this is one of them. I mean, we generated a large amount of hydronium here. And we'll end up with 0.0294 molar hydrogen oxalate. Okay, so here step 2 generated some quite a bit more hydronium. What about step 3? What would step 3 be? Step 3 is not going to be water, it's going to be Ka2 for oxalic acid. Oxalic acid is dichroic, and Ka2 is 10 to the minus 5, which is a lot bigger than 10 to the minus 14 for water. And so, you know, we saw that, hey, the step 2 generated quite a bit of hydronium. Maybe we should do step 3. So step 3 would be the second proton off oxalic acid coming off. And so that would be the Hc2O4 minus, the hydrogen oxalate ion, plus water, H2O liquid. This is going to give us hydronium and oxalate ion, C2O4 minus. Now, I look at the K. The K here is 5.3 times 10 to the minus 5. And so that K is not that big, so maybe I'm not going to get much, especially with the common ion effect. Moreover, if I look at the hydrogen oxalate concentration, what is the hydrogen oxalate ion concentration? It's only 0.0294. It's not that big. And so 0.0294 here, molar. Water, we ignore. Hydronium, the total hydronium now is 0.1294. And the oxalate's 0. Wait a minute, I didn't double check these. Can someone double check this before I spend time solving? We spend time solving that ice. Does it come out okay? It would be 0.0294 times 0.1294 divided by 0.0706. It comes out okay? Yeah, I think it comes out to a 5.38. Is that right? Times 10 to the minus 2. 5.38 times 10 to the minus 2 is good. That'll round to 5.4. So we're okay. So should we consider the additional hydronium that we get from this step? What do you think? Yeah? Okay. Well, let's just check it. If you're unsure, just go ahead and try it. Minus X molar, plus X molar, plus X molar. And so at equilibrium, we're going to get 0.0294 minus X, 0.1294 plus X, and X molar. And so the K here is going to equal the hydronium ion concentration times the oxalate ion concentration divided by the hydrogen oxalate ion concentration. And so this is going to be 0.1294 plus X times X divided by 0.0294 minus X. We'll just try the simplifying assumption. And so this is going to be 0.1294 divided by 0.0294 times X. Can someone solve for X? X is not going to equal Ka2. 1.2 times 10 to the negative 5. 1.20?
Yes.
Okay. 1.20 times 10 to the negative 5. Let's calculate the percent change. The percent change is going to be the change, x, over the initial. Well, x over the initial, we should take the smaller initial because that will give us the bigger percent change. And so this is going to be 1.2 times 10 to the negative 5 divided by 0.0294 times 100%. And so what does the percent change come to?
0.04.
Yeah, 0.04%, which means that the simplifying assumption was pretty good. It's pretty good because the K is not so big, 10 to the minus 5, and we have a lot of common ion. Right? The common ion keeps the oxalate and the additional hydronium small. And so when we look at the hydronium, it comes out to 0.1294 plus whatever we get from this step, which is going to be 0.0000012. So we end up with 0.129412 molar. Did this step really contribute much hydronium? No. In fact, if we calculate the pH after step 2 versus the pH after step 3, it's going to come out the same within rounding, right? And so it wasn't really necessary to do this. And so normally when you have a strong acid and weak acid, the weak acid is going to have a K like 10 to the minus 5 or something like that. It's not going to be a big contributor. You know, it's just when we have a weak acid that has a K like 10 to the minus 2 or something like that, then it might be significant.
What if you have a very dilute strong acid?
If you have a very dilute strong acid, then we run into the problem that we had a while back ago. If you have a very dilute strong acid, then the weak acid will be the most significant contributor. And so a very dilute strong acid and a very concentrated weak acid, the concentrated weak acid will be a significant contributor to hydronium. But we still do it the same way. But if we have a very dilute strong acid and a very dilute weak acid, then we're looking at simultaneous with Kw, because the hydronium ion concentration is going to be so small. And so we have different scenarios. The thing is, you just try it, and you just try it stepwise, and if it fails, then you don't. And so this one stepwise would have worked because this one really didn't perturb the previous step, right? And so step 3 doesn't really perturb step 2, because we didn't really gain much, and therefore we aren't really going to lose much here. But did step 2 perturb step 1? Does step 2 perturb step 1? Well, the concentration of hydronium changed significantly, 29.4. But step 1 is a strong acid, so it's a one-way reaction, right? So it doesn't perturb. All right, so that was the strong, what was that? Strong acid, weak acid. So if I had a scenario like HCl and acetic acid, then the acetic acid is really a negligible contributor. And the pH is going to be dictated solely by the strong acid, HCl. So that was a strong, weak. What other combination of acids do I have? Strong, strong. Strong, strong are very easy. And so, for example, if I had HCl and HNO3, let's say 0.100 molar and 0.100 molar. And so both of these are in the same beaker and they're both at 0.100 molar. Then the total hydronium is easy. Because, yeah, these don't perturb each other, so it's just going to be like Chem 1A, 0.200 molar. Right? Good. So strong acid, no problem. We could calculate the pH quite easily. As both of these are one-way reactions, both Kas are very large. Do we have to worry about Kw? You know, the most Kw is going to give you is 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. It's going to have no impact on this. So we look at that. And so strong acid is easy. Strong acid, weak acid, a little harder. And probably the hardest is going to be weak acid, weak acid. So if I take two weak acids and mix them together, that's This is much more of a headache. Well, it depends on the weak acids. And so we're going to have two scenarios here. For example, if acid 1 and acid 2 have very different Ks, like for example, the K for acid 1 is much bigger than the K for acid 2, you know, I shouldn't call it 1, or acid A, acid B. If the Ks are significantly different, then we can do it stepwise. We just look at all the hydronium ion contributors, and so. But if the Ks are comparable, that is, then we can't do it stepwise. If the Ks are comparable, we have to do it simultaneous. So let's look at a couple of weak acids. You know, if I had something like oxalic acid and acetic acid, then I could just do those stepwise. Most likely work okay. But if I had something like acetic acid and benzoic acid, so acetic acid, let's go with 0.100 molar, and the K for this is 1.8 times 10 to the minus 5. Then benzoic acid, which is C6H5COOH, 0.100 molar. Let's make the K, what's the K for benzoic acid? Does somebody have their book, Andy? Thanks. 6.3 times 10 to the negative 5. You see, these two Ks are pretty comparable. So that means both of these are going to be significant hydronium ion contributor. Whereas in a scenario like this, if the Ks are significantly different, like say one's 10 to the minus 2, the next is 10 to the minus 5, then for sure the 10 to the minus 2 is going to be the dominant source of hydronium here. And so what we try to do is we just try to do this stepwise. And so let's take the stepwise approach and see if that works or if it doesn't. And if we do this stepwise, we want to start off with the biggest hydronium ion contributor, which would be benzoic acid or acetic acid. Benzoic. Benzoic has a bigger K, so we start off with the biggest K, C6H5COOH. This is going to hydrolyze water, H2O liquid, to produce hydronium, and C6H5COO minus. C6H5COO minus is called the benzoate ion. And so initial 0.100, nothing's happened. Water, ignore. Hydronium and benzoate, 0. And so it's going to be minus X, so let's just go right down here. 1.100 minus X, this is going to be X molar, this is going to be X molar. Let's solve for X. So for benzoate, we got 6.3 times 10 to the minus 5, which is going to equal the hydronium times the benzoate ion, C6H5COO minus, concentration divided by the benzoic acid concentration. So this is going to equal X squared over 0.100 minus X. Pretty sure the simplifying assumption will work here. It's going to be X squared over 0.100. That means X is equal to 2.50 times 10 to the negative 3. And so this will be 0.100 minus 0.00250, which will give us 0.0975 molar. This will be 0.0025 molar, 0.0025 molar. And so we should just make sure that this works out. 0.0025 squared divided by 0.0975 gives us a K value of what? Six point four what? 41 times 10 to the negative 5. 6.41 times 10 to the negative 5 is supposed to be 6.3. What do you think? Good enough? It'd be nice if we were closer. Could it be because of the simplifying assumption? Yeah. You know, was the simplifying assumption valid? What was the percent change? This was a 2.5% change. What is the maximum percent change that we can have with the simplifying assumption? 5%. So this is kind of big. This is kind of big, but it's still okay. But since it's kind of big, that means our error is going to be bigger than what you'd expect. And so compare this to like 0.04%. When we had a 0.04% change, then the simplifying assumption worked fine and our K checked out, right? But the bigger this becomes and the closer it gets to 5, the more error we're going to have. So maybe this is okay, considering. But we just double check our answer for calc anyway. And so I think it's a bit off because of the simplifying assumption. Now, if we didn't use the simplifying assumption and you just use the quadratic, you should get a better answer. It's going to be slightly different. But we're all right. All right, so the next step is we want to figure out how much additional hydronium. Should we care? Do you think acetic acid will be a significant contributor to the hydronium? Yes or no? Yeah. Should I worry about the acetic acid in this mixture? Can I just say, oh, most of the hydronium comes from benzoic acid. I'm going to ignore the acetic acid. Can I do that? I can't do that because the K's these are pretty equal. And so the acetic acid will or should be a significant contributor. And so this is HC2H3O2, hydrolyzing water, this hydronium, and acetate. What we're going to do is we're going to carry down this to step 2. See what happens. And so initially I have 0.100 molar acetic acid from the beginning. And this is going to be 0.0025 and 0. Nothing's happened there. Minus plus plus, so this gives me 0.100 minus x molar, 0.0025 plus x, and then x. K equals 1.8 times 10 to the minus 5, which is equal to the hydronium times the acetate divided by the acetic acid. It's going to give 0.0025 plus x times x divided by 0.100 minus x. I'm going to try the simplifying assumption. So that goes to 0.025 divided by 0.100 times x. I'm going to solve for x. And what does x come out to? (7.2 times 10 to the negative 4). Ugh. So let's take the percent change. The biggest percent change will be 7.2 times 10 to the negative 4 over the smaller initial. This is going to be 0.0025 times 100%. 28.8%, which means that the simplifying assumption had failed, so can't do it. And so that means we'll have to use the quadratic equation for this. And so let's go ahead and do the quadratic for this. And so I want to get this into quadratic form. And so I'm going to get x squared plus 0.0025x is equal to, okay, so this is 10 to the minus 1 times 10 to the minus 5 is 10 to the minus 6. So 1.8 times 10 to the minus 6 would be 0.1234518. And then minus x times that is going to be this. It's going to be minus a 0.123418x. And then I'm going to add this and subtract this from both sides. So I'm going to get x squared plus 0.0025. How many decimals? 1, 2, 3, 4. 1, 2, 3, 4. And so I'll get a 1/8 here. X minus 0.123450 zeros and 1/8. This is equal to 0. Okay, somebody have their fancy calculator handy. Save us a lot of work. Quadratic.
If I did it correctly, it's 5.808 5 times 10 to the negative 4.
All right. 5.80 times 10 to the negative 4. Is that what you got to? Good. Okay, so let's try this here. This is going to be 0.100 minus, okay, times 10 to the negative 4 means I need 3 zeros and a 5/8. 0, so 0, 0, 0. This is going to give me 0.09942. 0.09942 molar. And then the hydronium, this is going to be 0.0025 plus 3 zeros, 1, 2, 3, and a 5/8. So this is 0.00308. And this would be a 0.00058 molar. So let's just check our calculation, make sure that it works out. 1.79 times 10 to the minus 5. So that rounds to 1.8, so that's good. You know, we didn't make the simplifying assumption here, and just use the quadratic, so this has got to be due to round off error. And so it's good. Should we consider the hydronium from water, Kw? Step 3? No, because water, the most hydronium we're going to get from water is 10 to the minus 7, but it's going to be a lot less than that because of the common ion effect. This is more like 10 to the minus 9, maybe. 10 to the minus 9 is not going to have any impact on this, right? Additional. So are we done here? Does it look good to you? No? Right, right. here, now, after step 2, we have this new concentration of hydronium, which means that the original hydronium we had in step 1 is no longer present, which means that this K is no longer going to check out, even though this was a little off, right? It's going to be way off now, which means that step 2 perturbs step 1, which means we have to solve this. Yeah, so weak acid plus a weak acid, if the K's are similar, we got to solve this simultaneously, which is quite a bit of work, right? How many equilibria do we have to solve simultaneously? Well, we have this one and this one. Do we have to worry about Kw here? Do we have to solve this K, that K, and Kw simultaneously? Or can we ignore Kw? In other words, do we have to solve 3 equilibria simultaneously or just 2 equilibria simultaneously? Just 2. Just 2 is correct. The time where we had to solve 3 equilibria simultaneously is when one equilibrium gave us hydronium, the other equilibrium gave us hydroxide, and we tied it all together with Kw. But in this case, both of these give us hydronium. And so Kw is not going to be a significant contributor to the hydronium here. So we don't have to worry about it. And so, this, must solve simultaneously. Because the hydronium in equilibrium 1 must be the same as the hydronium in equilibrium 2. They can't be different because they're in the same beaker. Okay, so that was a weak acid mixture. So we did strong acid, strong acid, strong acid, weak acid, and weak acid, weak acid. Those are the only combinations we have for acids, right? We could have some tricky ones. For example, what would you call this? H2SO4 plus HCl. You would call this a strong, and weak. It's a strong, and then weak. Because the first hydrogen comes off, H2SO4, that's a strong acid. But the second hydrogen is not a strong acid. HSO4 minus is weak acid. And so this would be a strong, weak type scenario. So H2SO4 is diprotic. And so how would we deal with this? We do it stepwise again. Maybe do HCl first, and then the first step of H2SO4, and then the second step of H2SO4. That should give us the total hydronium. Kw should be negligible in a case like that.
So that type of
I'm sorry? This type of equilibrium?
yeah.
Would be what?
Would that only apply to polychlorinated?
Yeah. It's like strong, weak? Yeah. Polyprotic that are strong for the first proton. All right, then we have this combo, which will be the base combos. So, what letter am I on now? E. So the base combos are just the same. We're going to have strong, weak, and weak. strong base is simple. You know, that's like Chem 1A, just add it up. Strong, weak, we just do it stepwise. You know, weak, that could be potentially simultaneous, depending on how different their Ks are. And so it's the same, except we're looking for hydroxide ion producers rather than hydronium ion producers. And we're dealing with Kb equations instead of Ka equations. But otherwise, it's the same. You know, Ka produces hydronium, Kb produces hydroxide. Okay. All right, so the next type of mixture, and these aren't in any particular order. In fact, I mixed them up. But the next type of mixture is going to be a strong acid, strong base mix. And so strong acid would be something like HCl, strong base would be sodium hydroxide. When we have HCl sodium hydroxide, we also give this another name, it would just be a titration. And so HCl plus sodium hydroxide, this is more like a Chem 1A problem, produces salt, sodium chloride, and water, each to a liquid. K for this reaction is what? Would it be very large? It would be 3 varies? Yeah. This is going to be very, very, very large. That's correct. And so we do it. But in Chem 1B, we're going to treat this mixture much more intensively. Since this is a special mixture titration, we're going to look at all possible combinations of HCl and sodium hydroxide. And the way we look at all possible combinations of HCl and sodium hydroxide is by mapping out something called a pH titration curve. In a normal titration, what you do is you put the acid in the flask and then you titrate it with base in the burette. Yeah, and you put an indicator in here, like phenolphthalein. But in Chem 1B, we're going to put something else in there. Do you know what else we're going to put in there? A pH probe. And it's going to be, well, Erlenmeyer is going to be tough. Is it easy to put a pH probe into an Erlenmeyer flask? No. And so we don't do the titration in an Erlenmeyer if we have to use a pH meter. What we do is we put it in a beaker and then we put a pH probe in here. And so in Chem 1A, you're only interested in one volume. The base is called the titrant, and that one volume is the, we'll call the endpoint volume. But in Chem 1B, what we want to do is we want to map out what happens as we add the titrant. Slowly do this. And so let's take a look at 0.100 molar HCl being titrated with 0.100 molar sodium hydroxide. And so we'll start off with 10.0 milliliters of acid here. If I stick the pH probe in 0.100 molar HCl, then the pH, it's 10 to the minus 1 molar, so the pH is 1.00. And so that's at 0 milliliters of sodium hydroxide. It's just the acid. And then what I do is I start adding the base slowly to this. As I add the base slowly, I'm going to neutralize some of the acid, but it's still going to be excess acid. And then all of a sudden the pH is going to shoot up and then stabilize again. At pH 7, this is what we call the equivalence point. This should be symmetric. And that's called the equivalence point, because that's where we've neutralized all the acid and we're just left with salt and water. This salt is neutral. Sodium chloride doesn't hydrolyze water. And so it's just pure water providing the hydronium in solution. All right, so if I have 10 milliliters of acid, how many milliliters of base will I need to neutralize it? If the acid and base are the same concentration, the 0.100, 0.100. 10 milliliters. And so the equivalence point is going to come at 10 milliliters. The equivalence point is where I've added just enough base to neutralize all my acid. I should be at pH 7. But phenolphthalein does not change color at pH 7. Do you know at what color phenolphthalein will turn pink? I mean, not what color, what pH phenolphthalein will turn pink? You might not know, but phenolphthalein doesn't turn pink until about pH 9. And so here's where you'll start to detect that pink color. And then it'll darken as we go up. And so about pH 9, we call that the end point of our titration. The end point is where the indicator changes color. And so ideally, we want the end point and the equivalence point to be exactly the same. Unfortunately, phenolphthalein doesn't cooperate because phenolphthalein won't change color until pH 9. And so that leads to an error, or does it? On the one hand, it leads to an error because this is about 2 pH units. pH is power function, powers of 10 function. So 2 pH units would be 100, 10 squared, yeah. So we're about 100 times off in terms of acidity. But on the other hand, the pH change is so dramatic here that when we look at the volume, you know, this curve rises steeply. And so the volume is just going to be a small error. And so a big error in pH translates to a very small error in volume because of the slope here. Whereas, you know, down here where the slope is nearly horizontal, a big error in pH would lead to a huge error in volume. And so, well, we're going to be a little bit off. How far off? Less than a drop, maybe? Or a drop at the most? You know, so negligible. Right. In Chem 1B, we're going to be interested not just at the end point, we're going to be interested in the whole thing. And so not only do we want to hit the end point, but we want to just continue until this flattens out. And so we're going to go well past the end point here. And so that being the case, what we're going to do is we're going to map out this curve in terms of equivalence points. The equivalence point will be at 10 milliliters. And then at half of that, which would be 5 milliliters, we're going to get something called the 1/2 equivalence point. And so we could subdivide this into different points. This would be the 1/4 equivalence point. The 1/4 equivalence point would come in at how many milliliters? 2.5. The 3/4 would come in at 7.5, etc. We could go beyond the equivalence point. Let's say we go to 15 milliliters. At 15 milliliters, we have what's called the 3/2, so the 1 1/2 equivalence point. And so we want to know, what's happening out there. And so we're going to map things out well before the equivalence point and well after the equivalence point, so that we see the entire curve. And the entire curve is going to look like this. This type of titration. All right, so we'll do some calculations now. We're going to calculate the half equivalence point. We'll calculate the equivalence point. We'll calculate the 3/2 equivalence point. And we're going to throw in one more here. One more right before the equivalence point. Right before the equivalence point, I'm going to call this the 9.99 out of 10.0 equivalence point. And so the fraction is 9.99 or 999 out of 100 equivalence points. In other words, this is going to be 99.9% neutralized. I'm only 0.01% away from neutralization, or 0.01 milliliters away from neutralization. Actually, how many mils is this going to be? Well, at the 9.99 out of 10 equivalence point, we're going to be 9.99 out of 10 times 10 milliliters. And so this is going to be 9.99 milliliters. Here. At the 3/2 equivalence point, this will be at 15.0 milliliters. At the equivalence point, will be at 10 milliliters. Okay, so let's do some calculations here to map out this. And so what's going to happen in the titration is this. You know, I start adding the sodium hydroxide, I neutralize some of the acid, but not all of the acid. And so in this region, we have excess HCl. We're going to have excess HCl until we hit the equivalence point. At the equivalence point, we've neutralized the HCl, so there's 0 HCl, 0 sodium hydroxide. And then once we go past the equivalence point, then we have excess sodium hydroxide going this way. And so this will be excess HCl, this will be excess sodium hydroxide. And here it's going to be stoichiometric, where we have just the right amount of both. I'll talk a little bit more on that. Break. And so the calculations for titrations are going to follow this pattern. This is the way I do it. The book uses millimoles. I like to do solution dilution first. If you do the book's method, you do millimoles and then dilute it at the end. I dilute it right at the beginning. And so what I'm going to do is I'm going to take this beaker. This beaker contains 10.00 milliliters of acid. And then I'm going to add the base to it. And so to get to the first, the 1/2 equivalence point, I need to add 5 milliliters of base. At the 0 equivalence point, that is, none of it's been neutralized. I know what the pH is, calculate in our head. And so plus 5.0 milliliters of sodium hydroxide, or base. And so this is going to give me a total volume of solution of 15.0 milliliters. And so the first step I have to do is step I. And so I want to calculate the new HCl concentration. The HCl is going to be a 10.0 over 15.0 dilution of 0.100 molar. And so in other words, it's 2/3 of 100, and that's going to be 0.066. I have 3 sig figs allowed, and I'm going to carry 1 extra. So quadruple 6 molar. The sodium hydroxide will be a 5.0 to 15.0 dilution of 0.100 molar. And this is going to give me 0.0333 molar. Okay, I'm going to, even though technically this is 2 sig figs, I'm going to use a different type of sig fig rule for this, dealing with the percentages. And so I'm going to carry extra digits. All right, after we do our step I, the next thing we do is step 1. Step 1 is always the same, whether it's chapter 16 or chapter 17. It's the strongest acid plus the strongest base. In chapter 16, I only had acid and water. If I only have acid and water, the strongest acid is going to be the acid, and the strongest base will be water. Or I would have base and water. If I only have base and water, then the strongest base will be the base and the strongest acid will be water. And so we only get Ka and Kb equations. In this chapter, we're going to get more variety. In this case, HCl is the strongest acid. Sodium hydroxide is the strongest base. This is going to form sodium chloride and water, get you to a liquid. K is very, very, very large. The HCl concentration is going to be 0.0666 molar. The sodium hydroxide is going to be 0.0333 molar. Sodium chloride 0 molar. And so the change is going to be complete. You know, strong acid, strong bases react to completion. So in this case, the limiting reagent is going to be sodium hydroxide. So we're going to lose all that. And that means we're going to lose 0.0333 molar, and we're going to be end up with 0.0333 molar here. And sodium chloride will end up at 0.0333 molar. Okay, 0.03, quadruple 3. Water is out of there. All right, so this looks like a buffer. Am I left over with a Henderson-Hasselbalch buffer, or is this an HH buffer? Because I have HCl, my acid, and its conjugate base. The conjugate base of HCl is chloride. And so I have my acid plus conjugate base. Is this an HH buffer? Yes? No? The answer is no. And why is it not a Henderson-Hasselbalch buffer? It's not because, I mean, that's related to it, but there's a simpler answer to why it's not an HH buffer. And that would be what? Because in order to be an HH buffer, the acid has to be weak and the base has to be weak. It has to be a weak acid, weak base combo. This is a strong acid and an incredibly weak base. And so this is not a buffer. In fact, sodium chloride, does sodium chloride hydrolyze water in any way? No, it's neutral. And so basically what we have is just an acid and water, just an acid solution left over. If we have an acid solution left over, and this is neutral, then all we look for are the hydronium ion contributors, right? And so the biggest hydronium ion contributor will be HCl, and then what would be the next biggest? Water. And so if I have a hydronium ion concentration of 0.03333, am I really going to worry about water? Not at all, because the most water is going to give me is like 10 to the minus 9, 10 to the minus 8, right? Which is not going to be significant. And so this is just an acid solution. It's a strong acid solution I'm left over with, like chapter 16. In strong acid, the pH is just going to be the hydronium ion concentration, which will be the negative log of 0.03333, which gives me a pH of 1. 1.47. Give me one more digit. So 1.477. Okay, which would round to 1.4. 1.477 means the pH went up just a little bit, right? We don't have as much acid because we've neutralized some of the acid, but the pH is still very low because okay, this is called the half equivalence point. Now we're going to go to the equivalence point. I'm going to skip the 99.9 or whatever percent equivalence point. We're going to go to the equivalence point, 100% neutralized. And so we need to add 10.0 milliliters of base. And so this is going to lead to 20.0 milliliters of solution. And so we have to do our solution dilution. HCl is going to be a 10 to 20 dilution of 0.100 molar. Well, 10 to 20 dilution is going to give me 0.0500 molar. And then the NaOH is the same. It's going to be a 10 to 20 dilution of 0.100 molar. This is going to give me 0.0500 molar. So let's go ahead and plug that in up here. This is 0.0500, 0.0500, and 0. Well, it's stoichiometric. This is what the equivalence point means. We have equal amounts. We're going to neutralize each other out, and we're going to be left with 0.0500 molar NaCl. What we're left over with is a neutral salt. And so the only hydronium ion contributor to this will be Kw. And we already know Kw. We don't have to do that because the pH will be 7.00, which is 7.00. That's at 10 milliliters of sodium hydroxide. Let's go to the 3/2 equivalence point. At the 3/2 equivalence point, we're going to add 15.0 milliliters of sodium hydroxide. And so the total volume would be the 10 plus 15 is going to be 25.0 milliliters. Figure out the new concentrations. The HCl is going to be diluted by 10 to 25 of 0.100 molar, which gives me 0.0400 molar. And the sodium hydroxide is going to be a 15 to 25 dilution of 0.100 molar, which is going to give me 0.0600 molar. And then we'll plug it into our table here. 0.0400, 0.0600, and 0. The change complete. The limiting reagent's HCl, so we go to 0 molar here. We're going to go 0.0200 molar here, and 0.0400 molar here. And so sodium chloride is neutral, so we can ignore that for pH. And so this is just the base solution. I have 0.0200 molar hydroxide. With 0.0200 molar hydroxide, do I have to worry about Kw, the next biggest hydroxide ion contributor to this? Would you worry about Kw? No. I mean, Kw, the most it's going to give us is 10 to minus 9, maybe, 10 to minus 8, something like that. 10 to minus 7 would be, but it's not possible. And so that's going to have no impact on this. And so what we'll do is we'll calculate the pOH. The pOH is the negative log of 0.0200, which gives us a pOH of 1.69? 1.69, give me one more digit. 8. So that means the pH will be 13.312. Is that right? 12.302. Thanks, man. 12.302. pH is very high. This is excess strong base, right? You expect a high pH for this excess sodium hydroxide. All right, so now we got the half equivalence, the equivalence, and the 3/2 equivalence point mapped out. We could map out more. And so the next point we had was the what we call the 99.9% equivalence point. Or in other words, it's 9.99 out of 10.0 equivalence point. And so we've neutralized 99.9% of our acid at this point here. And so let's take a look. That's going to be plus 9.99 milliliters of base. And so we end up with a total volume of 19.99 milliliters. for all these problems, I always start them over again. You know, each of these we treat as individual problems, even though it's the same titration. And the reason is, otherwise it gets messy if you try to jump from one calculation to the next, building up from the previous one. It's just easier to start all over again and do it here. And so the HCl is going to be a 10.0 to 19.99 dilution of 0.100 molar. Can somebody calculate that for me? The number's not going to be super clean, I think, but. Give me one more digit here.
2.
5.002 times 10 to the negative 2. The sodium hydroxide will be a 9.99 over 19.99 times 0.100. Send to the negative 2. They should be close, you know, because it's close to the equivalence point. But we just have a slight excess of acid. We haven't neutralized all of it. And so initial here, I'm going to just write this in decimal form. 0.005002 molar, and this will be 0.004997 molar. This will be 0 molar here. Okay, the change is going to be complete. Sodium hydroxide is a limiting reagent, so 0.004997. And so 0.005 is 0.04997 is 3.5. So this gives me 0.000005. Is that right? Do I have one extra 0? Is that right? Okay, thanks. The sodium hydroxide is 0, and this is going to be 0.00005 molar. Well, sodium chloride is neutral, so the HCl. Now, now do I have to worry about Kw? Would Kw be a significant contributor to this? Yeah? Well, this is actually 10 to the minus 5. Kw at the most is going to give us 10 to the minus. Actually, we can't get 10 to the minus 7 because there's no common ion at 10 to the minus 7. It's going to be less than 10 to the minus 7. And so it's going to be like 10 to the minus 8 or 10 to the minus 9. If we add 10 to the minus 8 or 10 to the minus 9, would that have any impact on this? No. And so I would say Kw is not significant. It would just, you know, where I'd start to worry is if this got to 10 to the minus 7 or 10 to the minus 8, then I'd start to worry Kw is going to be a significant contributor to this, right? But at 10 to the minus 5, I'm still okay. I don't have to worry about it. And so what is the pH going to be if we ignore Kw? It should be okay in this particular problem. .301. .301. 4.301. Okay, so in this pH titration, this is what we're going to see here. And let's try to put this in perspective. What's going to happen is the pH is going to stay kind of flat. It's going to go up a little bit, and then all of a sudden it's going to shoot up like this. And so at 10 milliliters, the pH is 7.00. At 9.99 milliliters, what is the pH? At 9.99 milliliters, the pH is 4.301. Do you see that? Because we just calculated the pH at 9.99 milliliters. Okay, what's the difference between this? The difference in milliliters is 0.01 milliliters. And so when we're at pH 4.3, we add 0.01 milliliters, and all of a sudden the pH will jump to 7.00. Now, how much is 0.01 milliliters? It's tiny, because you know what one drop is? You know how many milliliters one drop is? One drop is about 0.05 milliliters. Because there are about 20 drops in a milliliter. So if there's 20 drops in a milliliter, then each drop must be 0.05 milliliters. And so, you know how much water this, or how much titrant this is? This is 1/5 of a drop. And so, within 1/5 of a drop, the pH jumps from 4.3 to 7.0. I'm not drawing this to scale. This line is near vertical. It's got to be near vertical to shoot up that fast, right? And so I just kind of spread it out here. Is it possible to get 1/5 of a drop? Could you get, if you're doing the titration, could you get less than a drop? Is that possible or impossible? It's possible. How do you get less than a drop? Well, this is a Chem 1A technique. In Chem 1A, what you do to get less than a drop is you rotate the valve and then just hang a partial drop on the tip of the burette. That partial drop is not big enough to fall in. And you just hang it. So it's hanging there. And then you try to tap it in, but when you try to tap it in, it won't drop because it's not big enough. And so what you do is you grab your squirt bottle and you just squirt water in there and just wash it in. And that works. And so you can wash in. Maybe you could hang 1/5 of a drop on the tip of the burette and do this, right? Go from pH 4.3 to pH 7. But do you think you can get smaller than 1/5 of the drop? Let's say I want 1/100th of a drop. Is that going to be something easy? No. This is going to be, and so this is about as fine or as close as we're going to get to this, and so this calculation is okay. Now, if we could get 1/1000th of a drop, then we might have to worry about KW screwing things up, right? But in this case, we don't. And in fact, for all these titration problems, we don't have to worry about KW because KW will always be insignificant in these titration problems. The only time it's not is within like 1/1000th of a drop of the equivalence point. Does that make sense? All right, now in Chem 1B, you're not going to do this because if you grab your squirt bottle and start squirting water in, what's that going to do to the concentration? It's going to change the concentration, making it more dilute, which is going to change the pH. And so we don't want to squirt in water there. Once we start our titration and we're monitoring pH, if we add extra water there, then all of a sudden the pH just jumps up. And we don't want that to happen. And so Chem 1B, the smallest increment we're going to get is 1 drop. So if we're within 1 drop, well, the pH is going to be a lot lower than this. And so do you see how fast or how rapidly the pH jumps near the equivalence point? It's rapid. And so when I said that, there's a little bit of error. The equivalence point is at 7, but the end point with phenolphthalein is at pH 9. And so how much of a drop error is that? Well, that's less than 1/5 of a drop in error. No big deal. And so the end point and the equivalence point are essentially the same in terms of volume, but hugely different in terms of pH. Well, I need to talk about Thursday's lab, so let me talk about that briefly here. For Thursday's lab, we're going to titrate an unknown acid. The unknown acid could be monoprotic or diprotic. In Chem 1A, they told you if it's monoprotic or diprotic, what your unknown was. They marked it on the vial. You know, they said 1 proton or 2 protons, basically. 2 protons diprotic, 1 proton monoprotic. In Chem 1B, they're not going to tell you. But we can figure it out easily if we monitor the pH while doing our titration. Because in a monoprotic acid, what we're going to see is we're just going to see one equivalence point. And it's going to shoot up. You know, this is going to be like 6 or so pH units. And so there's going to be a huge change. You know, you start off down here at 1 or so, and then skyrocket up to 12, 13. There's a pH. And so 6 plus pH units. If it's a diprotic acid, the titration curve looks a little different. What we have is we have 2 equivalence points. The first one is not so dramatic, and the second one is a little more dramatic. It's like 3 or 4 pH unit jump, but not nearly as dramatic as the monoprotic here. It depends. It's a weak acid, so weak acids are going to start higher than 1. You know? And the first jump here is small. It's hard to detect, hard to see sometimes because the jump in pH is so small. And so we're going to have to come up with a procedure, keeping in mind things. So the first thing we need to do is this. We must dissolve your unknown in a minimum of water. It's a solid acid. And a minimum of water. The reason is because we want to start off at the lowest pH possible. And so the more concentrated the acid, the lower the pH. And that way we can maximize the first equivalence point. The first equivalence point for diprotic, let's say this is diprotic. The first equivalence point is not a very big jump. And so the lower the pH we start off, the better. The second equivalence point is not a problem. Now, what happens is if you use too much water, you're going to start off at higher and higher pHs. And so let's say we use too much water and we start off here, and we start adding base. When we start adding sodium hydroxide, the pH never goes down, right? And so here, the pH isn't going to go down and then catch the first. No, it's going to stay up there. We miss it entirely. pH is too high, so we don't see it. And therefore, the lower the pH you start, the more dramatic this first equivalence point will be. And so that's why we want to dissolve the acid in a minimum of water. But be careful about wasting too much time with dissolving it in a minimum of water, because we have one other thing we have to worry about. We have to adjust the amount of water so that the pH probe is submerged. When I say the pH probe, we're talking about the bulb on the pH probe, the little ball at the end. And so what we're going to do is, we can't do this in an Erlenmeyer. We're going to have to do this in a beaker. And we'll put the pH probe in here, like this. And at the bottom of the pH probe is the little glass bulb. That glass bulb has to be underwater or under solution. And so we have to adjust it here. And so this would be adequate. But if we did a great job and dissolved it in a minimum of water, and so we end up with something like this, where the bulb comes into minimal contact with the solution, we aren't going to get a decent pH reading. And so even though you spent a lot of time and did a great job, well, unfortunately you got to add more water because we don't have enough water to cover the bulb. All right, the next thing is we need to swirl this. Okay, so we're going to have the burette over here. We're going to have the pH probe here. And so we don't have, much room to swirl things around. And so we aren't going to swirl this by hand. What we're going to do is we're going to drop a little Teflon coated magnet in here. And this is called a stir bar, a magnetic stir bar. It's Teflon coated, so it's not going to react with anything. And then we're going to put the beaker on top of this. This is a magnetic stir. And so we'll just turn this on and that'll stir the bar. There's a magnet that rotates in this. We'll turn up the stir rate to the maximum, but we got to be careful because we don't want any solution splattering out of this. Okay, and then once we get everything set up, now we're ready to take our first measurement. Our first measurement will be the initial pH. And then we'll be taking pH readings as we go along. Since these are very steep, we have to take readings drop by drop. Because, let's say we take a reading here, 1 drop here, and then 5 drops later we take another reading, then we might miss this entirely. And so we have to take this drop by drop because we want to see, and this is going to happen within 1 or 2 drops. And so something like this, we have a drop here, and then a drop here, and a drop here, and it's done. And so we got to catch this. Well, in a typical titration, how many milliliters of titrant do you usually use? Your burette holds 50 milliliters. And so you typically hit the end point around how many mils? 35, 40 mils? We hit the end point at 35, 40 mils, maybe 45 mils here. But what we're going to do is we're not going to stop when we hit the end point. We're going to keep going. 3 halves, double, whatever. And so what we're going to try to do is we're going to try to hit this at 30 mils. If we hit the endpoint at 30 mils, then we can collect an additional 20 mils if we want of data here. And so altogether we might use about 50 mils of titrant. Well, 50 mils times 20 drops per milliliter is 1,000 drops. And so if we take 1,000 pH readings, what we do is we add a drop and then let it stir and stabilize the pH and then record the pH. If you take 1,000 readings here, are you going to finish in 3 hours? No, impossible. And so there's no way we can do this drop by drop. And so the compromise here is this. The compromise is we're going to take large intervals here, like a milliliter or half a milliliter. And then when we get close to the equivalence points, we're going to go drop by drop. Drop by drop. And so if this is 30 mils, around 30 mils, we want to go drop by drop to catch all of this. And therefore, at the half equivalence point, which would be 15 mils, we want to go drop by drop, right, to catch all of that. But the problem is this is an unknown acid. How do you know how many milliliters it's going to take to titrate an unknown acid? you aren't. And so what we have to do is we have to do a preliminary titration, which we call the trial titration. And so to determine the mass of acid required, we're going to do a trial titration. This preliminary titration, we aren't going to measure the pH. This preliminary titration is just going to be like a Chem 1A style titration. Okay, so for the trial titration, we need to take a guess at how many grams. But you know, you might guess too many grams. If you accidentally put too many grams in there, you're going to have to do multiple burette loads to titrate it, right? Which takes too much time. Or if you put too little. If you put too little, then you might hit the end point at like 3 milliliters. If you hit the end point at 3 milliliters, then you're going to lose a lot in terms of accuracy because of the error. 1 drop error in 3 milliliters versus a 1 drop error in 30 milliliters is a huge difference in terms of accuracy. And so what we're going to do in the trial titration is you're going to have a